So in section 2.1, the first thing we're going to introduce is what's called a frequency table or a frequency distribution. And what it does is it organizes information. So this says we're going to service times at a fast food restaurant, and we want to get a sense of, well, how long does it take to get through the fast food restaurant? And so they say, okay, so someone sits outside of the drive-through and they just have a timer, and they time how much each car takes to get from the order to the food to being gone. And they counted 8 cars, took between 1 minute and 2 minutes. Then they counted 24 cars, took between 2 minutes and 3 minutes, 13 cars between 3 minutes and 4 minutes. So does it make sense what they're trying to keep track of? Okay, so they're just counting. And that's what these frequencies are. So these frequencies here are just counts. It could be cars, it could be people, it could be anything that you could count as a whole number. Okay, so the first question is, how many individuals are included in the summary? So if they're looking for the total number of individuals, you just add the frequency numbers. Add frequency values. So you would just come in here and add these 5 numbers, and what you will get is 53 if you add those. So there were 53 cars that they counted going through the drive-thru. Now it says, is it possible to identify the exact values of all of the original service times? So what they're saying is, there were 8 people that it took between 1 minute and 2 minutes. Well, were all 8 of these 60 or 61 or 62 or 63 or 75 or 87? I don't know. So that's a drawback to a frequency distribution, is you lose the original information. So you lose the original data. Because I don't know. All 8 of these people might have taken 1 minute. All 8 of these people might have taken 1 minute and 19 seconds. So, or almost 2 minutes, I should say. So the answer is, can I get the original data? No. The data values in each class could take on any value between the class limits inclusive. So that just means that these 8 people might have had their service times anywhere between these 2 numbers, including those 2 numbers. So B is the best answer. The yeses are obviously gone. And then D is wrong because it says the frequency distribution tells nothing about the data values that fall below the lowest class limit or above the highest class limit. And I'll explain what these class limits mean. But what it says is, it doesn't tell us anything about the people that took less than 60 seconds. But here's how you build a table. If some people took less than 60 seconds, you add another row, and then you put their numbers in there. So it would only be by failure to make the table properly that you forgot to include anyone less than 60 or more than 4 minutes. Okay, if there's no questions on that, let's go to problem 2. So 2 has another frequency table, and in this one it is, I think this one was actors or actresses and the age they were when they won an award. Or maybe it's just people's ages when they win their first award. That might be it. And they had 27 people were between ages 5 and 9. 35 people were aged 10 to 14, etc. So the first question says, identify the lower class limits. So each one of these rows is what we call a class. So this is right here. This row is a class. And this row is a class. Each row is a class. Each row is a class. So the lower class limits are just the smaller numbers for each class. So all of these are the lower class limits. So it would be 5, 10, 15, 20, etc. Okay, if we call the numbers on the left the lower class limits, what do you think we call the numbers on the right? Yeah, the upper class limits, the UCLs, upper class limits. And so let's just record those. 9, 14. There's a pattern here. Each of these numbers is going up by 5, right? It's easier to see here, 5, 10, 15, 20. But if you look at these two, 9 to 14 is 5, 14 to 19 is 5, etc. And in fact, that's going to be the answer to the next thing. So what is the class width? The class width is 5. So it's the pattern to how do these numbers increase. So we can get there by saying 10 minus 5, or we can get there by saying 14 minus 9. In either case, we get a width of 5. Okay, identify the class midpoints. The midpoint is in between your two numbers. So what's in between 5 and 9? So to get this, you would add 5 plus 9 and divide by 2. So add these two numbers, the 5 and the 9, divide by 2, and you should get 7. Then do the next one, 10 and 14. Take 10 plus 14, divide by 2, and you should get 12. Beautiful. So you can save yourself a lot of work by saying, oh, by the way, these also go up by 5. So calculate 1, get it right. Now just add 5 to each one. 7, 12, 17, 22. Stop me if I make a mistake. 27, 32, 37. Sure. Yeah, so whatever this width was, these will also increase by that number. So yeah, you can definitely save yourself some work if you see that pattern. Okay, now there's something called class boundaries. And the class boundaries are typically half of a whole number below or above our limits. So the class boundary would be the number that's just smaller than 5. And we would say it's 4.5. And now this is where it gets a little tricky because these boundaries, it depends on your numbers. So if these are whole numbers, which I think in this class there almost always will be, you go half of a whole number, so you go 0.5. But if you do other things, especially more scientific numbers where they're not whole numbers, you might have the boundaries be different. But for us, it's pretty much always going to be just half of a 0.5 above or below. So 4.5 would be the lower boundary. It's the number just to the left of 5. 9.5 would be the upper boundary here because it's the number just to the right of 9. Now 9.5 is the in-between for both the 9 and the 10. It's right in between those two numbers. So the next one we would look at is what's the number just to the right of 14? 14.5. Good. But what do you notice about this pattern? Yeah, they also go up by 5. So again, all I need to do is get one of them right, and now I can just add 5 to each. And if I've done it correctly, my last number should be just half of a unit above the biggest number. And it is. Okay, last question is, how many individuals are included in the summary? Well, we did that in the last problem. How did we do it? Yeah, that's exactly right. So to find the total number of individuals, you add all these numbers. And if you do that, you will get 87 for this one. So 87 people were considered in this study, and they broke them into their classes. 87. That is nearly all of the theory we need today. Is it make sense? Is it pretty clear?
So the frequency is a number of.
Yes. Yep. That's exactly right. So the frequency is just how many people fit into this class. 27 people fit into the ages 5 to 9. Yep. Okay, if we're good with that one, let's look at 3. So in 3 it says, does the frequency distribution appear to have a normal distribution? So normal distribution might be one of the most important concepts in the entire class. And it is, if you plot this information, it should look something like this. So we're going to plot this data. And it should look something like that when we do a bar graph with this information. And what this is, you go to the x-axis to the left, the x-axis to the right, and then you try to smoothly connect the middles of each bar. And it should look something like this. And this is called a normal distribution. Has anyone heard it called a different name? And I didn't draw it great. This is probably the name you've actually heard it called before. It's called a bell curve. And it's called a bell curve because it kind of looks like an old-fashioned bell. And the idea here is that, so in the middle here, this would be your average value. So most people are average whatever you want to do. Average height, average weight, average IQ, average run speed. I mean, almost every aspect of humans falls on a bell curve, where you have a bunch of people that are average, a few people that are really above average, and then a few people that are below average. So this is an important shape. We're going to use it many, many times in this class. So to figure out this one, we have to kind of plot this data. So let's take a look. It's a little hard to do freehand, but just try to get the axes as to scale as you can. So we need 1, 2, 3, 4, 5, 6, 7 classes. And then our highest frequency is 14. So let's go as high as 15. And then we can kind of decide how many tick marks we want. One, 2, 3, 4, 5, 6, 7, 8. So let's go by 2. And then this actually becomes 16. Just trying to get a rough scale here. And then this first one would be 40 to 44. And then this one would be 45 to 49. 50 to 54. Etc. I won't write the other ones in. I'll just write the last one in. 70 to 74. Okay, now we'll just plot this. So the first one has a height of 3. So I go up to 3, which is right here, and I draw a bar over and down. So this has a height of 3. This one has a height of 0, so the next bar is just flat on the axis. The next one has a height of 4, so we would go to 4. Next one has a height of 14, so it's all the way up here. Then we go to 8. Then 5. And then 1. So it looks roughly like that. Did everyone see how I got that? I just want to make sure you see how I did it. that each of these numbers is the height of each bar. That's the main takeaway here. So these frequencies are now the heights of each bar. And this is a famous thing that we just did. This is called a histogram. And a histogram is just a picture that shows the heights of each of these frequencies, of each of these classes. And this will be another important thing we study in this class. So with histograms, we can tell if the distribution is normal. If it's normal, then we have all sorts of math tricks we can use with it. But that's the question. Does this shape look like this shape? Yeah, so if I were to connect the dots on this, I'd put a dot here, and then try to go through each center. So if I kind of remove the bars and just try to recapture that shape, what it looks like is this. And now I can ask, does this look like that? Hopefully everyone in here would say no, right? So this does not look like that, therefore it is not normal. So no, the distribution does not appear to be normal. C. Good on that one? Okay. You will have to do some quick sketches in this class. That's just something you're going to want to get used to. The next one is pretty simple. We want to build the frequency table. So in this one, we have body mass index values for 20 females. Construct this frequency distribution, beginning with a lower class limit of 15, so they started at 15, and use a class width of 6. So from 15, add 6 to it, get to 21, add 6 to it, get to 27, etc. But you don't have to even build this because they did it for you. So they did the hard work for you. You're left with the easy work. So all you have to do is organize these 20 numbers into which class it should go to. And so the way I like to do it is just start with the first number, 17.7. It's in between 15 and 20.9, so make a tally there and cross off 17.7. Then 33.5 would be right here between 33 and 38. Tally, cross it off. 26.5 would go here. 24.3 would go here. 25.9 there. And you can get pretty quick with this. Go ahead and do it at your desk and correct me if I make a mistake, and we'll see how we do. When you get to 5, you do a dash through the whole. You do 4, and then at 5, you do a dash through those 4. Okay, so so then the last step is to convert these tallies to numbers. So 3 tally marks, that's a frequency of 3. This is 5 plus 4, that's 9. This is 4. This is 3. This is 1. So I get 39431. Did anyone else get those numbers? Okay, a few people nodding their heads. Good. So that's how you do it. You just organize those numbers. Now, as a check, you should add these numbers up and see if they total 20. So we would say 3 plus 9 plus 4 plus 3 plus 1. And if you add these up, you will get 20, which is a good check to make sure you didn't miss a tally, because that can be easy to do. Okay, 5 is the exact same. So I won't sit here and do it. I'll just give you the answers. But first we should find out, well, how many numbers do they have? This is rainfall in inches for 1 month. So they have 1, 2, 3, 4, 5, 6 columns. And they have 1, 2, 3, 4, 5 rows, which means there are 30 values here, just multiplying those two numbers. So there's 30 numbers, which will be what we use to check our answers. And you just go through again. 0.36 would go right here in the second one, etc. Cross them off. If you do that, you should get 22, 5, 2, 0, 0, 0, 1. And it's okay to have zeros in here. In fact, you should. So if your biggest number is 1.27 right here, but you don't have 3 other numbers before that, you still need to capture that 1.27. So you just have placeholders. Otherwise, your graph gets messed up. It's going to be missing. It's going to make a jump. So one of the keys to all this is that the width should be the same. So my graph, it only looks correct if each of these x-axis tick marks represents the same jump in numbers, 4 units or 5 units or whatever you pick. Okay. Now, that's the answer to the first part. The second part says, does this look normal? Well, how do we check if it looks normal? We have to plot it again. So we have to plot this. Now, I'm not actually going to take the time to plot it because I've already shown you how to do one. But basically the first, let's see, we've got 1, 2, 3, 4, 5, 6, 7 again. The first one is way up at 22. It's a really big number right off the bat. 22 height. Then the next one goes down to 5. So let's say it's down here. Then the next one's 2. Then I've got 3 zeros. And then the last one is 1. So I can quickly sketch that without getting too caught up in axes and making my scale perfect. And I think we can all quickly connect these dots and look at the shape. Does that shape look like a normal curve, which should look like this? Hopefully you would all say no, right? Hopefully you can pretty quickly say, wait a second, this shape does not look like that at all. So once again, is this normal? We would say no, so the yeses are gone. The distribution is not symmetric and the frequencies do not start off low. That's true. Let's see if there's a better answer. No, although the distribution is approximately symmetric, the frequencies do not start off low, increase to some. So this is also, this second part's true, but although the distribution is approximately symmetric, let's talk about what that means. Symmetry means if I draw a line down the center of something, one half is a mirror of the other half. Okay, that's symmetric. There's in no way I can get symmetry from this one. There's no way I can pick some center point and fold one half onto the other. So this one is definitely not symmetric. So when they say it's approximately symmetric, they are not correct. No, although the frequencies start low, increase to some maximum, then decrease, the distribution is not symmetric. So this one's almost correct. It is not symmetric, that's true. But did we start off low here? No, we started off with a 22. We started off with a really big number. But if you look at it, these words are correct. Starts low, so this is low. The height is low. Goes to some maximum, here's the maximum. And then decreases and goes low again. That is the words for a bell curve. Low to some maximum, then low again. But this one starts high and then goes low. So that's why this one's wrong. D's wrong. Does not start low. Questions on that one? That might be a good problem to study because it has you build a frequency distribution and then plot and then analyze the shape.
So it's A, it's true.
Oh, yep, it's A. Thank you. Okay, 6 is going to introduce the idea of a relative frequency table. Construct a table that includes relative frequencies based on the frequency distribution shown below. Then compare the amounts of tar in non-filtered and filtered cigarettes. Okay, so they give us a table down here where they're looking at the milligram levels of tar in either non-filtered cigarettes or filtered cigarettes. And they build these frequency tables. So we've really got two tables here, one for non-filtered, one for filtered. The first thing you want to do is add up the frequencies and find out how many cigarettes did they look at. So if you add these numbers, you should get 25 for this one, and then 25 for this one. Now to convert this from a frequency distribution to a relative frequency distribution, all we have to do is convert these numbers to percentages. And you'll notice that they have percent symbols for each of these spaces. So to do that, we just have to take each number divided by the total. So this first blank here would be 2 divided by 25. So we would take 2 divided by 25, and you'll get 0.08. Yep. Mm-hmm.
Is that actually going to be there? Because that one says 19 to 24, where the top line is 7 to 12.
Boy, it is hard to get anything past you guys. That's perfect. Well done. So if you just blindly take 2 divided by 25 and get 0.08, which would be what as a percentage?
8%.
8%, and you stick it in the first blank, you will get it wrong. And why will you get it wrong? Because it starts at 19 through 24. So you need to put this 8% in the 19 to 24 down here. So we put 8% there. But what does that mean for these other two? What should we put here? Yeah, 0, because there were no non-filtered cigarettes that had those levels of tar. So very good catch. Okay, now that we've started at the right place, everything else should match up. So if I go, the next number I'm going to have to calculate is 1 divided by 25. And if you do that, 0.04. And to get to percent, we just move the decimal 2 to the right, or call it 4%. So this one's 4. The next one's going to be 13 divided by 25. 0.52, or 52%. And I'll assume you can get the rest. I'll just give you the solutions. So if you continue this pattern, 6 divided by 25, 3 divided by 25, you should get 24 and 12. And as a check, what should these numbers add up to? If you've done it correctly, these should add up to 100%. And they do, if you add them up. Okay, now to finish this table, it's the same thing. You'd have 2 divided by 25, 2 divided by 25, 6 divided by, etc. And what you would get for those numbers are 8, 8, 24, 60. Now, in the filtered cigarettes, they don't go above 25 to 30. So what should I put for these last 3 blanks?
0.
Zeros. Perfect. Once again, add these up, and you will find that they add to 100%. So you're confident your numbers are correct. Okay, now we can answer the more important question of, do cigarette filters appear to be effective? Well, we can probably agree that tar in your lungs is bad, right? So what do we want? We want less tar. So if you look at this, the tar of all the filtered cigarettes is below 30 milligrams. The biggest numbers for the non-filtered cigarettes are above 30 milligrams. So if you kind of just try to visualize it, you've got most of your numbers on the low end for your filtered cigarettes and most of your numbers on the high end for your non-filtered. So does it appear to be effective? I would argue yes. You're cutting off, these filters are cutting off all these big levels of tar, right? They don't go above 30. If they weren't effective, these numbers would be much closer to each other. So the two bubbles would be much closer to each other. So yes, it's effective. So let's get rid of these no's. Looks like only one answer works because it says this cannot be determined, but I argue it can. So A. Yes, they appear to be, they've shifted the entire numbers to the lower end of the spectrum. Okay. Stop me if you have a question, otherwise I'll keep moving forward. 7 says construct a cumulative frequency distribution. So we got to kind of get our keywords here. This was a relative frequency distribution. Relative frequency, think percent. Cumulative, what this truly means is, cumulative means add as you go. Add as you go. So they give us the temperatures, the daily low temperatures, and they give us a frequency distribution, but then they want the cumulative frequency. So they start with saying, how many daily lows were less than 40? Well, there was one. There was only one day that had less than 40. Then it says less than 45. Well, these two were less than 45, but also this one was. So this would be 3. Yep, 1 plus 2. Then it says less than 50. Well, these 4 are less than 50, but so are these 2, but so is this one. So it would be 1 plus 2 plus 3. Or excuse me, 4. 1 plus 2 plus 4, 7. Okay, less than 55. 15 plus 4 plus 2 plus 1. So it's 1 plus 2 plus 4 plus 15, or 22. Now there's an easier way to do this than what I'm showing. So let's do the next one the easy way. Less than 60 would be what? 22, my previous answer, plus how many, plus my next number, which is 5. 27. Then less than 65 would be my previous answer, 27, plus the next number, which is another 5. 32. Then my final answer should be my last answer, 32, plus the last number, 1, 33. But what you're truly doing is this pattern here. You're just continually adding. So you start with the first number. The next answer is the first number plus the second. The next number is the first number plus the second plus the third. Does that make sense? So you're just continually adding the next number to the list. Now to check this, you should add these up. And they add up to 33. These two numbers should match if you've done it correctly. So that's a cumulative frequency distribution. You're just adding the numbers as you go. All right, 8. I've seen this question trip up students in the past, so let's take it slow and please ask me questions if you get confused. I've seen this one trip students up on the homework. Natural births randomly selected from 4 hospitals in a highly populated region occurred on the days of the week in the order of Monday through Sunday with the frequencies 52, 64, 72, etc. Does it appear that such births occur on the days of the week with equal frequency? So first they want us to build a relative frequency table. To do that, let's first identify these frequencies next to each day. So the first one's Monday, so let's write 52 here. The next one stands for the number of births on Tuesday, so 64, 72, 58, 59, 43, and 52. Now you would add these numbers up. And if you do that, you would get a total of 400. So there were 400 births. And they're split across the 7 days of the week with these numbers, with these frequencies. Now, how do we change these numbers to relative frequency numbers? Just divide by 400. So let's just divide each of these by 400. That total we just found. And that will get them into percentages. And if you do this, I'll just write a couple. You'll get 0.13, 0.16, etc. They're going to want them as decimals, or excuse me, as percentages. So this would be an even 13%, 16%. You'll get 18% for Wednesday. Thursday, the decimal turns out to be 0.145. So that's 14.5%. Don't miss the decimal there. Yeah, I think on this one they want you to count 2 decimal places. So these first ones will come out evenly as whole numbers, but then this one has a half on it. And the next one I think has an even more interesting number. It's 0.1475. So you would take that whole thing, 14.75. The next one turns out to be 10.75. And then the last one is another 13%. And again, these should add up to 100. And they do. Now, this one asks, so that would be the answer for the first part, getting those frequencies right. The next part asks to plot it again. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. But if you look at these numbers, they're all pretty close, right? 13 and 16 are pretty close. So Monday's going to be just slightly lower than Tuesday. And Tuesday's going to be just slightly lower than Wednesday. Then Thursday is above Monday but lower than the other ones. This next day is almost the same. This day's 10, so it's down about the lowest. And then the last number is back to 13. So just very roughly, that's what it looks like. So we would ask, do they appear about equal frequency? Well, here's what equal frequency would look like. Here's what equal frequency would look like. This would be completely equal. Well, is this pretty close to that? For us, I would argue it is. Okay. For us, I would argue this is. And this is a special distribution. It's called a uniform distribution. And it's interesting because it does govern things like births for sure. But what's more interesting is they use it for lotteries. So if you were to track the lottery numbers that won, you have 10 digits to look at, 0 through 9. Those 10 digits, if you plotted them, should look roughly normally, or excuse me, uniform. If they didn't, and if you notice, wow, there's a spike in the number 5, well, now you should play 5 in your lottery numbers more often because you have a higher chance of winning. So it does show up. So did this appear equal? We would say yes. It appears the bursts occur on the days of the week with frequencies that are about the same. Sounds good to me. B. So no's are out. Impossible to determine's out. Yes, it appears that bursts occur on the days of the week with frequencies that are exactly the same. Well, that's not quite true. They're not exactly, but they're pretty close. Questions on that one? Okay, 9 and 10 are typically just vocab word ones, so let's take a look. They should be pretty simple. Fill in the blank. Blank are sample values that lie very far away from the majority of the other sample values. So if we plotted height, if we plotted people's height, actually the height would be down here, and this would be the frequency. And we had most people were on this normal curve. And then way over here, we had someone who in the class who was 8 foot tall. They would show up as a little bubble over here because they're the only person that's 8 foot tall. And that is called a, anyone know? Good. So that's called a outlier. Of course, it works the other way too. If we had most people in here around average height, but then we had someone who is 4 foot tall, they would be way over here on the left. They would also be considered an outlier. But it's basically someone who is outside of the majority of where people are. And it's true for all sorts of things. What's that? Actually, this is asking the same thing. So it's outlier. Frequencies are the heights of these bars, right? These are bars that you then connect into a smooth curve. So the frequency is the height of the bar. Notice this outlier, its frequency is only 1, really, because there's only one person way out there. But this person is far away from the group. This is the group over here. That's what an outlier is. Okay, last one, 10. Class width is found by, well, how did we find the class width? So subtracting the smallest value in the data set from the largest value in the data set. If you subtract the largest value in the data set and the smallest value in the data set, that is called range. It's equal to max minus min. Well, range is not the same as class width. So A is out. Subtracting a lower class limit from the next consecutive lower class limit. That is one way to do it. In fact, that's how we did it. In our example, we took 10 minus 5, and we got a width of 5. So that's how we did it. Subtracting the lower limit of one class from the upper limit of that same class. We actually never did that for any of those questions. And then the last one is adding the lower class limit to the upper class limit and dividing by 2. What was that one? That's what we did to find the midpoint. Remember, we added the 4 plus the 9 and divided by 2 and got 7, or I can't remember the numbers we had now. 10 and 4 maybe, and we got 7. So that was a midpoint. Okay, that's it for section 2.1.